Hello, everyone. In this video, we're going to be talking about Newton's universal law of gravitation. And this law of gravitation just states that two masses will exert a gravitational force on each other. So they're going to attract each other. For example, if this is mass A and this is mass B, whatever the masses may be, if I draw a free body diagram for mass A and mass A is going to feel a gravitational force provided by mass B, and mass B is going to feel a gravitational force provided by mass A, and these two gravitational force on A, the magnitude will be equal to the force provided by B as well. Okay, so this is consistent with Newton's third law of motion, which says that for every action there's an equal and opposite reaction. So if this is an attractive force, if this is an attractive force, this one will be in the opposite direction of equal value. Okay, so there's an equation that goes along attached to this. So the equation here is F sub g is equal to gravitational constant times mass number 1, mass number 2, divided by the distance between those two masses squared. Now be careful to measure the distance correctly. When you measure the distances between the two masses, you look at the center of mass. So when you're looking at r, you're looking at this distance right there. Okay, most of the time you'll be given this distance from surface to surface. That is not r. Okay, you still have to add the distance from this surface here to the center of the planet. You have to add that, and the surface over here to the center of the planet. So obviously this is on a larger scale, but if this was something a smaller mass, you wouldn't have to add that. You were going to assume that the other masses are small, very, very, very small particles. Therefore, you don't have to add their inner radius. Okay. So remember that the gravitational constant obviously is a constant, has a value of 6.67 times 10 to the negative 11. Okay. And obviously its units are going to be Newton meter squared over kilogram squared. Okay. And that's always going to be the same. M1 and M2, so I'm just going to write M, are just the mass of the objects. Mass of objects. And for the mass of the objects, we use kilograms. R is a distance between centers of masses. Okay, it's the distance between the centers of masses, and that's going to be measured in meters. Okay, and obviously F sub g, we can do lowercase g, is the gravitational force. So gravitational force, and that is measured, and all types of forces are measured in newtons. Okay, so whenever we're looking at universal law of gravitation, this just means that that law applies um, to anything in this universe. Okay, that's a big, big, big comment. All right, so in this video, we're going to do two examples. One of them is going to be from your TIPS assignments, and the other will be an actual calculations one. So let's go ahead and jump into the TIPS worksheet that you're going to see with the day that I'm on. So looking at this first problem, at problem 92, it says that two asteroids with masses of m and 3m exert a gravitational force on each other. A student contends that the forces will be in different directions and of different magnitudes as shown below. So what's wrong, if anything, with the student's contention? If something is wrong, identify it and explain how to correct it. If the student's contention is correct, explain why. So this is obviously wrong. The reason this is wrong is because when we talk about forces, the force on A due to B, the magnitude must be of equal value to the force of B due to A. Sorry, this absolute value sign. Okay, they must be of equal value. This is consistent with Newton's third law, Newton's third law of motion. Okay, remember that for every action there's an equal opposite reaction. It's not correct to say that if this force, let's say, was 10 newtons to the left, it will do a negative value. It's not correct to say that this force is 30 newtons, right? Although that may be the misconception here, because this mass is a mass of m, and this mass is 3 times as much as that. Okay, that is not correct to say that. If this mass has a force of negative 10 newtons to the left, then obviously this one will have also 10 newtons, but instead it'll be to the right. So this is not correct, and that's the reason why it is not consistent with Newton's third law of motion. So we're going to skip around to another type of problem. So let's look at problem 94 here. It says that three objects, each with a mass of m, exerted gravitational forces on each other. Which of the following arrows below shows the direction of the net force on mass B? So we're looking for the net force arrow on a specific mass, and that mass is mass B. So we're going to focus our attention. We're going to focus our attention to mass B. Okay, so we're going to draw a free body diagram for that. So mass B has two forces exerting on it. So we're going to look at it right here. Okay, one of them is going to be in this direction. And that is a force of gravity due to on B due to C. And there's another gravitational force by the other mass, and that is the gravitational force on B due to A. Okay, so when I do the free body diagram here, I will have a two-dimensional force. All right, so to find the net force, F net, I do it as a vector, I must add force B on A to the vector force B C. Okay, so when I do this, remember that I have to draw this first vector out. So I'm going to do this one in this direction, something like that. This is force on B due to A. And then I add the tip of this one to the tail of the next one. So the next one is pointing in this direction here. So I get the tip to the tail, and I do that. And that is a force B to C. And these are obviously both vectors. So when you're trying to find the net force, you're going to find what we call the resultant vector. This here is the net force vector. Okay, so in this example, we can see that the direction of this net force is going to be consistent with option number one. Okay, and your reasoning would be to add vectors. Okay, we would add vectors, and these forces are attractive. They are attractive. Remember that gravitational force cannot be repulsive. All right. So let's jump to number 96. Object A has twice the mass of object B. So this one is twice as much as that one. Okay. So identify the pair of force vectors, the arrows, that correctly compare the gravitational force exerted on A by B and that to B by A. Okay. So we already stated that Newton's third law says that for every action there's an equal and opposite reaction. So the arrows must be of equal lengths. For that reason, we can eliminate A, we can eliminate C, we can eliminate E, and that's it. Now, remember that the gravitational force is always attractive. Okay, so on this table on this column on the left side, we're looking at the gravitational force on A by B, and on this other side, we're looking at the gravitational force on B by A. So if we look at this picture, the gravitational force provided by B is to the right. Okay, so for that reason, we can eliminate D and F, and B here would be a correct answer, and it makes sense because they are attractive. They are attractive, okay, and that is consistent with uh, gravitation. Okay, so let's move on to a calculations type of problem, and this is more of a relationship between force and distance, force and mass, and pretty much proportion. So let's go over the equation one more time. Remember that, let me go back to the pen here. Remember that the gravitational force is equal to G m over r squared. So in this case, the relationship is that Fg, one of the relationships is that Fg is inversely proportional to 1 over r squared. So whatever change happens to r, Fg feels the square of that change. Why? Because r is being squared. Another relationship that you'll see is that F sub g is proportional to the product of the masses. If one of these doubles and the other one, then Fg doubles as well. If they both double, then Fg quadruples. So in this example, we're going to see some of those changes, and we're going to see what happens to the gravitational force. So let's read the problem. It says, explain the changes in the gravitational force, if any, caused by changes in the masses and distance between the masses in the following scenarios. Use the universal law of gravitation to explain. In letter A, it says both masses are doubled and the distance is also doubled. Okay, so in this case, both of the masses are doubled. Okay, so I will double each mass, and the distance is also doubled. So then I look at r being doubled before it's squared. So on this side, we see a change of 4 on the top side. We can eliminate the m's and the r. But on the top side, we see a change of 4, and 2 is squared. Okay, 2 is squared. So on the bottom, in denominator, you see a change of 4. So what is the total change in fg? It gets multiplied by a factor of 1. That means that fg does not change. Okay, sorry, let me go back. So fg remains constant. All right, and that'll be the answer for number 1. Let's try another one, see if it makes a little more sense. One mass is decreased by a factor of 4 and the distance remains constant. So in this equation, we're looking at the relationship between Fg and the product of the masses. One of these masses decreased by a factor of 4. In other words, it got multiplied by 1/4. Okay. Remember, Fg is directly proportional to the product. So whatever happens to one of the masses, or to both of them, that's what happens to Fg. So Fg in this case is going to get multiplied by a factor of 4. We can also say that Fg decreases by a factor of 4. Okay? Why? Because one of the masses was decreased by a factor of 4. So letter C. One mass is doubled and the other is cut in half while the distance is tripled. So in this equation, we're going to look at this proportion here, m over r squared. One of those masses is doubled, so I'm going to double this left one, it really doesn't matter. And the other one is cut in half, so I'm going to multiply this one by half. And while the distance is tripled, so I'm going to triple r and square it. So let's see what happens in the numerator. 2 times half is just 1, right? That number cancels with that one, so we just have 1 in the numerator. Divided by 3 must be squared. Okay, so 1 over 9. So what is the change in Fg? It changes by a factor of 1 over 9. Okay, these are the proportions that they'll test you on the exam. So letter D, distance is increased by a factor of square root of 2, and one mass is doubled. Okay, so again, m over r squared. Notice I don't put equal to, it's just proportional to. So one of these masses is doubled, so I double this one, and the radius, or the distance between them, is multiplied by square root of 2. So in the numerator, all I have is 2. Denominator, I square that square root of 2, so that square root just cancels, so in the bottom I have just 2. So therefore, Fg changes by a factor of 1. In other words, it remains constant. So letter E, masses remain constant and distance is quadrupled. So I write this proportion one more time. So let's get used to doing these types of things. If you can pick this up, the proportions, everything else will be easy from here on. So the masses remain constant, so they're multiplied by 1, so it's the same number, but the distance is quadrupled. So almost quadrupled r. So in the numerator, I have a change of 1. In the denominator, I have a change of 4 squared, so 16. So then Fg changes by a factor of 1 over 16. Letter F, distance is tripled and both masses decrease by a factor of 3. So write the proportion one more time, m over r squared. Both masses are decreased by a factor of 3. So in the numerator, we multiply this by 1 over third, 1 over third again because each drops by a third, and the distance is tripled. So in the numerator, I have 1/3 times 1/3, we just have 1 over 9, divided by 3 squared is 9. This is just the same thing as saying 1 over 9 times 1 over 9. So this is just 1 over 81. So by doing this, the gravitational force changes by a factor of 1 over 81. And the last one is one mass is tripled. So Fg proportional to m. We don't need to do over r. I mean, we could write it R is not going to change in this case. One of these masses is going to get tripled. So the numerator I have a change of 3. The denominator, I did not do anything to it. So 3 over 1. So this gravitational force just changes by a factor of 3. Alright, so I hope this kind of puts everything together. This whole lesson here and a few examples, obviously from the tippers and from one of the other worksheets on number 11. If you can understand this, the rest of the worksheet or the practice will be very, very simple. So thanks for watching, and this was Newton's universal law of gravitation. See you.